Hey physics class, I'm going to start working through this problem. I'm going to do the first two segments before the assignment is due, and then you'll have the last two as a solution for afterwards. So you'll have the first two kind of like as a hint to get you going, and then when you're all done, you'll have the last two to refer to. So here we go with the first one. Okay, so the information we have is that this segment is 30 meters long, right? And that this is completely vertical. So that means that we're dealing with a 90-degree angle. Okay. So that said, here's all the things that we have to deal with. We have a mass of 1 kilogram. This will be true for all of them, but it's just good to rehearse this information. We've got a coefficient of friction of 1.1. And the force that's pulling something down the slope is going to be equal to mg sine of theta, and the force of friction opposing that is going to be equal to the coefficient of friction times mg cosine of theta. Okay, so on this particular part of the slope, we're dealing with a 90-degree angle, and that means that it's being pulled down here with mass, gravity, and then the angle. Now the sine of 90 is 1. That's 1. So this whole thing is just 9.8. And so that means we've got a force downwards of 9.8 newtons. What about the force of friction? Well, the force of friction is the coefficient times the mass times gravity times the cosine of 90. But since the cosine of 90 is 0, it means that all of that is 0. There is no friction to hold that back. And that means that is the sum. That's the net force on the object, 9.8 newtons for 30 meters. Well, luckily, because our mass is only 1 kilogram, that 9.8 newtons also means an acceleration of 9.8 meters per second squared. So if we want to know how fast it's going right there, we just need to use that equation 2a delta x equals v2 squared minus v1 squared. We're looking for that v2. That's going to be the square root of 2a delta x, which in this particular case is equal to the square root of 2 times 9.8 times 30. Let's just get that. 2 times 9.8 times 30 square root. All right, so 24.2. I guess I'll keep the extra decimal point just in case I need it for later. 24.2. So we can go ahead and say at this point right there, that velocity is equal to 24.2 meters per second. Okay, that's going to be our initial velocity going into the next segment. This segment wasn't really that complicated because the angle was 90 degrees, and so the sine and cosine were just 0 and 1. It's the next one that's really going to be interesting. So 24.2 is the velocity. Let's just keep that in mind as we go to the next segment. Okay, so this next segment is making a 60-degree angle with the horizontal, right? So there's that vertex there, and this is a 60-degree angle. Again, The length is 30 meters, as before. So now, when we're doing mg sine theta, we're going to have some different values. Remember, that's the force pulling it down. That is now going to be equal to 1 times 9.8 times the sine of 60. It's less than 9.8 now, but exactly how much less? So if we do the sine of 60 and multiply that by 9.8, I'm getting 8.49. Okay, so that's the force pulling down that slope, right? 8.49 newtons. What about the force of friction holding it back up? So that one is going to be coefficient times mg times cosine theta. And so that is, coefficient is 1.1, mass is 1, gravity is 9.8, and then it's by the cosine of 60. Well, the cosine of 60 is 1/2. Luckily, that's one of those easy to remember ones, but I'm still going to enter it into the calculator, just for consistency, times 9.8 times 1.1. 5.39. That would be the force of friction keeping it back. So we've got 8.49 pulling it down, 5.39 pushing it back up. That means that we have a net force of 8.49 minus 5.39. 8.49 minus 5.39, 3.1. Once again, happily, because the mass is 1, that force is just the same as the acceleration. And that means that we can now calculate the speed at the end of that little leg. That's going to be, once again, using this equation. Okay, so if you'll recall from our previous page, the velocity at the beginning was 24.2. We're looking for that velocity right there. So essentially we're solving this hold on, that's just a tad behind the line. That's right, you can still see it. 2a delta x equals what we're looking for squared minus 24.2 squared. Now that one you can't see. Here, I'll get out of your way. Oh, not that one. There you go. There you go. So we just have to solve for this. So I think I've got some space over here. I'll use that. So V2, if I could, spare you the algebra, is going to be equal to the square root of 2 times 3.1 times 30 plus 24.2 squared. So let's go ahead and work that out. 2 times 3.1 times 30. That's 186. Oh boy, I really am running out of room. Equals the square root of 186 plus, let's see what 24.2 squared is. 24.2 squared. Woo! 585.64. 585.64. Okay, so if I add 585.64 and 186, and then I take the square root, that's my new velocity, 27.8. All right. Well then, so we started at velocity of 0, accelerated to 24.2, and then accelerated to 27.8. That's the velocity right there. I'll mark it again in red just like I did the last one. 27.8. Okay, so this is your model for doing all of the other problems, okay? When you're trying to find the final velocity after a leg, you know, one of these little segments, I should say, you need to know the initial velocity, you know, which would have been the velocity that the last one ended on. You can use that in v1 squared in this equation. You're looking for that. And if you're given that and you're looking for that, you're going to need to know those. Now, the delta x is easy. It's 30 for everything. The a, though, that one's the trick. In order to find the acceleration, you need to find the net force. The net force is going to be mg sine theta minus coefficient of friction mg cosine theta. So if you can find out how hard gravity is pulling down on it with that equation, and how hard friction is working to keep it from sliding from that equation, if that's stronger, then it's speeding up. If that's stronger, then it's slowing down. Since that's stronger, that means that this 3.1 newtons is making it speed up, which means that acceleration of 3.1 meters per second squared is making it speed up. So I should add to 24.2. I ended up adding, looks like 3.6 meters per second. When you do this next segment right there, you're going to find that the friction is probably stronger than the pull down now. Okay? Well, I'm going to stop this recording here, and then I'll finish the problem in another video. Good luck.